Welcome to Slumbertainment. Get comfortable, close your eyes, and let yourself relax. Tonight we explore the history of the space race. Please like and subscribe for more restful content. Now, let's begin. The story of humanity's reach toward the stars begins not in the quiet laboratories of peaceful scientific inquiry, but amid the chaos and destruction of the Second World War. In the closing years of that global conflict, as nations mobilized every resource toward victory, a new kind of weapon emerged from the shadows of Nazi Germany that would fundamentally alter the trajectory of human civilization. The V-2 rocket, standing nearly 50 feet tall and capable of carrying a ton of explosives across more than 200 miles, represented a technological leap that transcended its brutal purpose. Designed under the direction of Wernher von Braun and his team of engineers at Peenemünde on Germany's Baltic coast, these missiles climbed to the edge of space itself before arcing down toward their targets in London, Antwerp, and other Allied cities. Though they arrived too late to change the outcome of the war, these rockets demonstrated that the barrier between Earth and space was no longer an impenetrable wall, but merely a threshold waiting to be crossed. The V-2 was born from dreams far older than the conflict that gave it life. Von Braun himself had been inspired as a young boy by the writings of Hermann Oberth and the science fiction of Jules Verne, imagining journeys to the moon and beyond long before such ideas seemed remotely feasible. His team of rocket engineers shared this vision, even as they found themselves forced to pursue it under the auspices of a regime committed to conquest and destruction. The irony was not lost on von Braun, who later reflected that he had aimed for the stars, but kept hitting London instead. The V-2 itself was a marvel of engineering for its time, using a liquid fuel mixture of ethanol and liquid oxygen, guided by gyroscopes and a primitive analog computer, reaching speeds that exceeded the sound barrier by a factor of 4. Each launch was a controlled explosion, a barely contained violence that pushed the boundaries of what materials and human knowledge could withstand. As the war drew to its conclusion, in the spring of 1945, both the Soviet Union and the United States recognized the immense strategic value that German rocket technology represented. In a frantic race, American forces swept through Germany as part of Operation Paperclip, a secret program designed to capture German scientists and their research before the Soviets could claim them. Von Braun and more than 100 of his colleagues surrendered to American troops, bringing with them not only their expertise, but also crates of documents and partially assembled rockets. The Americans relocated this precious cargo to the White Sands Proving Ground in New Mexico, where the captured V-2 rockets would be reassembled, studied, and launched throughout the late 1940s. Meanwhile, Soviet forces captured the Peenemünde facilities and brought their own contingent of German engineers eastward, along with complete manufacturing equipment and rocket components. The stage was being set for a competition that would define the next 2 decades. In those early post-war years, few could have predicted that rocket technology would become the focal point of superpower rivalry. The United States and Soviet Union emerged from World War II as the world's dominant military and economic powers, their alliance of convenience quickly dissolving into mutual suspicion and ideological confrontation. The development of atomic weapons had already introduced a terrifying dimension to this emerging Cold War, but rockets promised something even more strategically significant: the ability to deliver those weapons across intercontinental distances in a matter of minutes. What had begun as a project to understand and replicate German achievements soon transformed into parallel programs of escalating ambition and capability. The Soviets, under the direction of chief designer Sergei Korolev, threw themselves into rocket development with a determination born partly from necessity, as they lacked the long-range bomber fleet that gave America a a strategic advantage in the early Cold War years. Korolev was in many ways von Braun's counterpart, a brilliant engineer whose own passion for space exploration had survived years of imprisonment in Stalin's gulags during the late 1930s. Released during the war to contribute to the Soviet aviation effort, Korolev emerged from that nightmare with his dreams intact, but his health permanently damaged. His vision extended far beyond military applications, though he understood that only by delivering onto the Soviet Union's strategic needs could he hope to pursue his ultimate goal of human spaceflight. Through the late 1940s and early 1950s, both Soviet and American programs made steady progress, developing increasingly powerful rockets, testing guidance systems, and pushing the boundaries of what was possible. The Americans conducted their work relatively openly, with von Braun becoming something of a public figure, writing articles for popular magazines about the coming age of space exploration, and even consulting on a series of Disney television programs that captured the public imagination. The Soviet program, by contrast, operated in almost complete secrecy. Korolev himself was never identified by name in Soviet media, referred to only as the chief designer, his identity a state secret. This opacity served both security purposes and the Soviet preference for presenting technological achievements as products of the collective rather than individual genius. Yet behind this veil of secrecy, the Soviet program was making remarkable strides, developing the R-7 Semyorka, a massive intercontinental ballistic missile that would prove capable of far more than its designers initially intended. By the mid-1950s, both nations possessed the key ingredients for something unprecedented: powerful enough rockets, miniaturized nuclear warheads, and the engineering knowledge to potentially send objects beyond Earth's atmosphere. What had begun with the brutal V-2 attacks on London had evolved into something with implications that stretched far beyond military strategy, touching on questions of national prestige, technological supremacy, and humanity's place in the cosmos. The transformation of rocketry from a purely military concern into a contest for supremacy in space occurred with startling suddenness on the 4th of October, 1957, when the Soviet Union successfully launched Sputnik 1 into orbit around Earth. The satellite itself was remarkably simple, a polished sphere of aluminum alloy, just 23 inches in diameter, weighing less than 200 pounds, equipped with 4 whip-like antennas and a radio transmitter that broadcast a steady beeping signal on frequencies that anyone with basic radio equipment could detect. Yet this modest device, circling the planet every 96 minutes at an altitude that varied between roughly 150 and 600 miles, represented an achievement of staggering significance. For the first time in history, humanity had placed an artificial object in orbit, had extended its reach permanently beyond the atmosphere, had demonstrated that the dreams of spaceflight were not merely the province of science fiction, but achievable reality. The satellite's radio signal, that simple beep, 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 could be heard by amateur radio enthusiasts around the world, an audible proof that the space age had begun. The American reaction to Sputnik was one of genuine shock mixed with a profound sense of vulnerability. If the Soviet Union could place a satellite in orbit, the reasoning went, then they could certainly deliver a nuclear warhead to any location on American soil. The technological achievement represented not just a scientific milestone, but a strategic revolution, one that seemed to call into question American assumptions about its own technological superiority. Newspaper headlines spoke of a Sputnik crisis, and politicians from both parties demanded explanations for how the United States had fallen behind in such a critical area. The launch triggered immediate soul-searching about American education, particularly in mathematics and science, and led to unprecedented federal investment in technical training and research. President Eisenhower, though privately more measured in his response than the public rhetoric suggested, recognized that the United States needed to demonstrate its own capabilities quickly. The pressure intensified just 1 month later, when the Soviets launched Sputnik 2, a much larger satellite weighing over 1,000 pounds and carrying a passenger, a dog named Laika, who became the first living creature to orbit Earth, though she would not survive the journey. The American space program in late 1957 was divided and underfunded, split between competing military service branches, each pursuing their own rocket programs with limited coordination. The Navy had its Vanguard program, designed to launch a small satellite as part of the International Geophysical Year, a collaborative scientific effort involving nations around the world. The Army had its own program under the direction of Wernher von Braun, whose team had been developing the Jupiter-C rocket with capabilities that von Braun insisted could have beaten the Soviets into space if only they had been given permission to try. The Air Force pursued its own missile and satellite initiatives, and rivalries between these programs sometimes seemed as intense as the competition with the Soviet Union itself. In the wake of Sputnik, the pressure to launch anything into orbit became overwhelming. The first attempt, using the Navy's Vanguard rocket in December 1957, ended in spectacular failure when the rocket rose only about 4 feet before settling back onto the launch pad and exploding in a fireball that was captured by television cameras and broadcast around the world. The press dubbed it Kaputnik and Flopnik, and the humiliation was complete. Finally, on the 31st of January 1958, the United States succeeded in placing its first satellite into orbit. Explorer 1, launched atop a Jupiter-C rocket from Cape Canaveral in Florida, was smaller than even the first Sputnik, weighing just over 30 pounds, but it carried scientific instruments that would make an important discovery. Under the direction of physicist James Van Allen, Explorer 1's instruments detected intense zones of radiation trapped by Earth's magnetic field, regions that would come to be known as the Van Allen radiation belts. This discovery demonstrated that satellites could serve purposes beyond mere propaganda or military reconnaissance, that they could expand human knowledge in fundamental ways. Yet even as Explorer 1 represented a recovery of American prestige, it was clear that the space race was only beginning, and that the Soviets maintained a significant lead in launch capability. Their R-7 rocket, the same vehicle that had launched both Sputniks, was far more powerful than anything in the American arsenal, a consequence of the Soviet need to lift their heavier nuclear warheads, which in turn reflected their less advanced miniaturization technology compared to American weapons design. Through 1958, both nations continued launching satellites with increasing frequency and capability. The Americans established NASA, the National Aeronautics and Space Administration, in October of that year, consolidating civilian space efforts under a single agency and clearly separating scientific space exploration from military missile programs, though the line between them would always remain somewhat blurred. NASA inherited facilities, personnel, and ongoing programs from its predecessor, the National Advisory Committee for Aeronautics, and immediately began planning for increasingly ambitious missions. The Soviets, meanwhile, continued their program under the same veil of secrecy that had characterized their efforts from the beginning, with Sergei Korolev still unnamed and unknown to the world, but driving his teams toward ever more spectacular achievements. The competition had evolved from a simple demonstration of rocket capability into something far more complex, involving national pride, ideological rivalry, technological development, and genuine scientific exploration all tangled together in ways that were sometimes complementary and sometimes contradictory. The launches became more sophisticated rapidly. Satellites grew more capable, carrying cameras for reconnaissance, instruments for studying space radiation and magnetic fields, and communication equipment that would eventually revolutionize global telecommunications. Yet even as these practical applications emerged, both nations were already looking beyond satellites to the next milestone, one that would capture imaginations even more powerfully than the first orbital achievements. The goal was to send something beyond Earth orbit entirely, to reach toward the moon and perhaps even to touch its surface. The race was accelerating, driven by a combination of military imperatives, scientific curiosity, and the very human desire to be first, to plant a flag, whether literal or symbolic, in new territory. The beeping of Sputnik had announced the space age, but that was merely the overture to a much longer and more complex performance that would unfold across the decade to come. The transition from Earth orbit to lunar exploration represented a quantum leap in difficulty and ambition, requiring not just more powerful rockets, but entirely new techniques for navigation, communication, and spacecraft control across distances that dwarfed anything attempted before. The Moon, though Earth's nearest celestial neighbour, lies on average about 240,000 miles away, a distance so vast that radio signals travelling at the speed of light take more than a second to traverse it. Reaching the Moon demanded precise calculations of trajectory, accounting for the gravitational pulls of both Earth and Moon, the momentum of Earth's rotation, and the Moon's own orbital motion. It required spacecraft that could function for days without maintenance, that could withstand the extreme temperatures of space, that could transmit data across interplanetary distances with equipment that by modern standards seems almost impossibly primitive. Yet both the Soviet Union and the United States committed themselves to this challenge with an urgency that reflected both the symbolic importance of lunar exploration and the belief that whoever mastered space would hold decisive advantages in the Cold War rivalry that structured their relationship. The Soviets struck first in the race to the Moon, as they had with satellites. In January 1959, Luna 1 became the first spacecraft to escape Earth's gravitational pull and enter orbit around the Sun, though it missed its intended target of impacting the Moon's surface. This near miss still represented a historic achievement, demonstrating that Soviet engineers had mastered the complexities of launching a spacecraft on an interplanetary trajectory. The mission carried instruments to study the solar wind, cosmic rays, and the magnetic fields in space beyond Earth's immediate vicinity, returning valuable scientific data even as it failed to reach the Moon itself. More significantly, Luna 1 proved that the enormous distances of space exploration were not insurmountable, that careful calculation and powerful enough rockets could send human-made objects on journeys that had been purely theoretical just years before. The psychological impact was considerable, reinforcing the impression that the Soviet Union held a commanding lead in space capabilities and suggesting that America was perpetually catching up rather than competing as an equal. Success came 7 months later when Luna 2 crashed into the Moon's surface on the 13th of September 1959, becoming the first human artifact to reach another celestial body. The spacecraft, intentionally designed to impact rather than orbit or land softly, struck somewhere in the Mare Imbrium region, one of the dark plains visible from Earth that ancient astronomers had mistaken for seas. Luna 2 carried Soviet pennants, metal ribbons emblazoned with the hammer and sickle, which presumably scattered across the lunar surface upon impact, a symbolic claiming of territory, even though international agreements would later establish that no nation could legally claim sovereignty over the Moon. The mission confirmed that space between Earth and Moon was largely empty, contradicting some theories that had proposed the existence of substantial dust clouds or radiation belts that might impede travel. Just weeks later, Luna 3 achieved another first by travelling around the far side of the Moon and photographing the hemisphere that is forever hidden from Earth's view, revealing a landscape remarkably different from the near side, heavily cratered and lacking the large dark maria that characterise the Moon's Earth-facing hemisphere. The American program struggled to match these achievements, hampered by less powerful rockets and a series of frustrating failures. The Pioneer program, initiated even before NASA's creation, attempted to send probes toward the Moon throughout 1958 and 1959 with limited success. Some failed to escape Earth's gravity, others lost contact or experienced malfunctions, and the program became a source of embarrassment as the Soviets continued to notch historic firsts. Yet these failures, though painful at the time, taught American engineers crucial lessons about spacecraft design, about the unexpected hazards of space travel, about the need for redundancy in critical systems, and the importance of rigorous testing. The American approach increasingly emphasized reliability over rapid achievement, accepting that this might mean falling behind in the short term, but would eventually yield more consistent results. This philosophy reflected broader differences in how the two space programs operated, with the Soviet program willing to accept higher risks and more frequent failures in pursuit of propaganda victories, while the American program, operating under intense public and congressional scrutiny, felt pressure to avoid spectacular public failures, even if this meant more conservative timelines. Throughout the early lunar exploration efforts, both programs generated scientific knowledge that expanded human understanding of the Moon and the space environment. Measurements revealed that the Moon lacks any significant magnetic field, suggesting the absence of a liquid metallic core like Earth's. The surface appeared to be covered in a layer of fine dust, created by billions of years of meteorite impacts, a finding that raised questions about whether this dust would support the weight of a landing spacecraft, or if vehicles might simply sink into it. Radiation measurements refined understanding of the hazards that human travellers to the Moon would face, particularly from solar flares that could release deadly bursts of high-energy particles. Temperature readings showed that the lunar surface experiences wild extremes, baking in direct sunlight at temperatures above the boiling point of water, then plunging to hundreds of degrees below zero in shadow. Each mission, whether successful or not, added pieces to a puzzle that would need to be substantially complete before anyone could seriously contemplate sending humans on such a journey. The competition intensified as the 1950s gave way to the 1960s, with both nations announcing increasingly ambitious goals. President Eisenhower, though more cautious about space spending than some of his advisors and critics wanted, authorized expanded NASA budgets and approved development of more powerful rockets. The Soviets, flush with their string of space successes, began speaking publicly about ambitious plans that included not just unmanned lunar exploration, but eventual human missions to the Moon and beyond. Sergei Korolev, still unnamed in Soviet media, was already designing spacecraft intended to carry cosmonauts around the Moon and eventually to its surface, though he faced significant technical challenges and resource constraints that were not apparent to outside observers. The space race had evolved from a competition to launch satellites into Earth orbit to something far more expansive, a contest to demonstrate mastery over interplanetary space and to claim symbolic possession of the Moon itself. Neither nation could back away from this competition without appearing to concede technological and ideological inferiority, and so the race accelerated, drawing in ever more resources, recruiting thousands of engineers and scientists, and capturing the imagination of millions of people around the world who followed each launch and each achievement with an attention that no purely scientific endeavour had ever commanded before. The question of whether to send humans into space, as opposed to continuing with unmanned probes and satellites, sparked considerable debate within both space programs and among the scientists and engineers who understood the enormous challenges involved. Robotic spacecraft could be designed to withstand conditions that would kill a human being, could be launched on trajectories that accepted high risks of failure and required no provisions for life support, no return journey, no elaborate safety systems. They were cheaper, lighter, and more expendable. Yet there existed a widespread belief, perhaps more intuitive than rational, that human spaceflight represented the true measure of a nation's space capability, that sending people into orbit and beyond carried a significance that no unmanned probe could match. This belief drew partly from the heroic tradition of exploration, from the notion that true exploration required human presence and human judgment, and partly from the propaganda value of demonstrating that one's citizens could venture into space and return safely. Both nations concluded that human spaceflight was essential, and both committed themselves to programs that would attempt to place their citizens in orbit as quickly as possible. The Soviet program moved first, shrouded as always in secrecy, but driven by Korolev's determination to achieve human spaceflight before the Americans. The program to send a cosmonaut into space, designated Vostok, faced immense technical challenges, beginning with the fundamental question of how to keep a human being alive in the hostile environment beyond Earth's atmosphere. Space is a near-perfect vacuum where unprotected human tissue would boil and freeze simultaneously, where radiation from the sun and cosmic rays strike without the filtering protection of atmosphere, where temperatures swing between extremes depending on exposure to sunlight. The spacecraft would need to maintain breathable air at appropriate pressure and temperature, would need to remove carbon dioxide exhaled by the cosmonaut, would need to provide water and food, and would need to protect against radiation. Beyond these life support requirements, the spacecraft needed reliable systems for orientation and maneuvering, for firing retro-rockets to slow down and begin the descent back to Earth, for surviving the intense heat of re-entry when atmospheric friction would raise the spacecraft's exterior to temperatures that could melt steel. Korolev's design for the Vostok spacecraft reflected both brilliant engineering and necessary compromises forced by limited time and resources. The spacecraft consisted of two sections, a spherical re-entry capsule where the cosmonaut would ride, and a service module containing equipment, batteries, and the retro-rocket system. The re-entry capsule was deliberately simple, a sphere because that shape would be stable regardless of its orientation during re-entry, covered with ablative material designed to char and burn away, carrying the heat away from the interior. The cosmonaut would remain inside this sphere, strapped into an ejection seat for the entire mission, which would last only long enough to complete a single orbit of Earth. There would be no ability to maneuver the spacecraft significantly, no way to change orbits or adjust the trajectory except for the crucial retro-rocket burn that would slow the spacecraft enough to begin its fall back to Earth. The cosmonaut would be more passenger than pilot, along for the ride on a journey whose success depended almost entirely on systems functioning automatically or under control from the ground. Before risking a human life, the Soviets conducted a series of test flights using dogs as passengers, building on their experience with the unfortunate Laika, who had perished aboard Sputnik 2 when her life support system failed. These test flights revealed numerous problems and led to several failures, including missions where the spacecraft ended up in wrong orbits, or where recovery systems malfunctioned, leading to the death of the animal passengers. Yet gradually the reliability improved, and by early 1961, Korolev felt confident enough to propose a manned flight. The selection of cosmonauts had begun 2 years earlier, drawing from Soviet Air Force pilots who underwent rigorous medical and psychological testing, centrifuge training to prepare them for the intense accelerations of launch and re-entry, and practice with the cramped confines of the Vostok fatigue capsule. The chosen candidate for the first flight was Yuri Gagarin, a 27-year-old senior lieutenant whose calm demeanour, photogenic appearance, and impeccable political credentials made him an ideal representative for the Soviet Union. On the 12th of April 1961, Gagarin climbed into the Vostok 1 spacecraft atop an R-7 rocket at the Baikonur Cosmodrome in Kazakhstan, the launch site whose very existence was officially secret. As the countdown proceeded toward launch, Gagarin reportedly remained remarkably relaxed, joking with the technicians and controllers, displaying a confidence that may have been partly genuine and partly performance. When the rocket ignited and began its climb towards space, Gagarin exclaimed, "Poyekhali," a Russian colloquialism that translates roughly as "off we go" or "let's go," words that would become famous worldwide. The rocket performed flawlessly, accelerating Gagarin to orbital velocity and releasing the Vostok spacecraft into an orbit that ranged from about 100 to 200 miles above Earth's surface. For 108 minutes, Gagarin circled the planet, experiencing weightlessness, observing Earth through the spacecraft's small portholes, and conducting simple observations and tests, while ground controllers monitored his condition anxiously. He described Earth as blue, reported that he could see clouds, mountains, and large rivers, and expressed wonder at the beauty of the planet from space. The return to Earth was fraught with tension as the automatic systems fired the retro rockets to slow the spacecraft and begin its descent. The service module was supposed to separate from the re-entry capsule, but failed to do so cleanly, remaining partially attached and causing the combined assembly to tumble violently as it encountered the upper atmosphere. Eventually, the connecting cables burned through from atmospheric heating and the capsule stabilized, though Gagarin experienced moments of genuine fear during the tumbling. At about 20,000 feet, as planned, Gagarin ejected from the capsule and descended separately by parachute, landing in a field near the village of Smelovka. The capsule landed nearby under its own parachute. Local farmers who witnessed his landing reportedly approached with considerable confusion, confronted with a man in an orange spacesuit who had fallen from the sky. Gagarin reassured them that he was Soviet, not an alien or an invader, and within hours the world learned that the Soviet Union had achieved yet another spectacular first, that a human being had orbited Earth and returned safely, that the space age had entered a new and even more dramatic phase. The news of Yuri Gagarin's successful orbital flight reverberated around the world with an intensity that surprised even those who had anticipated a significant reaction. In the Soviet Union, Gagarin became an instant hero, his smiling face appearing on posters and in newspapers, his achievements celebrated as validation of Soviet technological prowess and the superiority of the socialist system. Premier Nikita Khrushchev recognized the propaganda value immediately and milked the achievement for all it was worth, hosting elaborate celebrations and sending Gagarin on goodwill tours to dozens of countries where he was received like visiting royalty. The cosmonaut's humble origins, his disarming charm, and the sheer audacity of his accomplishment made him a genuinely popular figure even in Western nations, though this popularity also served Soviet interests by presenting a human face to a system that the West often portrayed as totalitarian and oppressive. For the United States, Gagarin's flight represented another painful demonstration of Soviet space superiority, coming less than 4 years after Sputnik and reinforcing the impression that America was perpetually one step behind in the space race. The American response combined genuine admiration for Gagarin's achievement with renewed determination to catch up and eventually surpass the Soviet program. NASA's own human spaceflight program, Project Mercury, was already well advanced by the time of Gagarin's flight, with 7 astronauts selected and trained, spacecraft built, and test flights completed. However, the American approach emphasized caution and incremental progress, planning to conduct suborbital flights before attempting a full orbital mission. The first American in space, Alan Shepard, would not orbit Earth, but would instead be launched on a ballistic trajectory that would carry him just beyond the edge of space before he fell back to Earth about 300 miles downrange from the launch site. This 15-minute mission, though significant, could not match the drama and achievement of Gagarin's full orbit, a fact that NASA and the American government understood would diminish the impact of their accomplishment. Nevertheless, they proceeded with their planned schedule, and on May 5, 1961, less than a month after Gagarin's flight, Shepard climbed aboard the Freedom 7 spacecraft atop a Redstone rocket at Cape Canaveral. Shepard's flight, though brief, demonstrated American capability and introduced the American public to the experience of spaceflight through extensive media coverage that the Soviets had not permitted for Gagarin's mission. Television cameras captured the launch, and millions of Americans watched as the rocket lifted Shepard away from Earth, accelerating him to speeds over 5,000 miles per hour. During his few minutes of weightlessness at the top of his trajectory, Shepard reported his observations, tested the spacecraft's manual controls, and experienced the profound sense of awe that comes from seeing Earth's curvature and the blackness of space firsthand. His splashdown in the Atlantic Ocean and recovery by helicopter went smoothly, and though the mission achieved only a fraction of what Gagarin had accomplished, it restored some measure of American confidence and demonstrated that NASA's methodical approach was producing results. 3 months later, Gus Grissom repeated the suborbital mission successfully, though his spacecraft sank after splashdown when the hatch blew prematurely, nearly causing Grissom to drown before rescue helicopters could pull him from the ocean. These early spaceflights revealed both the possibilities and the profound dangers of human space exploration. The astronauts and cosmonauts sat atop rockets containing thousands of tons of explosive fuel, trusting their lives to complex systems where any single failure could prove fatal. They experienced accelerations during launch and re-entry that pushed the human body to its limits, forces that made breathing difficult and could cause blackouts if not managed carefully. They depended entirely on their spacecraft's environmental systems, knowing that any breach in the pressure hull or failure of oxygen supply would kill them within minutes. They faced the psychological challenge of confinement in tiny spaces with no possibility of rescue if something went wrong, knowing that the slightest miscalculation in trajectory or timing could strand them in space or cause them to burn up during re-entry. Yet both American astronauts and Soviet cosmonauts approached these risks with remarkable calm, sustained by thorough training, by faith in their equipment and support teams, and perhaps by the same spirit that had always driven explorers into unknown territories despite the dangers. The Soviet program continued to demonstrate its lead through the remainder of 1961 with the flight of German Titov aboard Vostok 2 in August, a mission that extended to a full 17 orbits, proving that humans could function in weightlessness for more than a day and sleep in space without apparent ill effects. Titov's mission, however, also revealed a troubling phenomenon that would become known as space adaptation syndrome, as the cosmonaut experienced nausea and disorientation during the flight, symptoms that would affect many subsequent space travelers as their bodies struggled to adapt to the absence of gravity. The Americans, meanwhile, worked toward their own orbital mission, refining their Mercury spacecraft, training their astronauts in simulators that replicated the experience of launch and re-entry, and conducting unmanned test flights to verify that their Atlas rocket, more powerful than the Redstone used for suborbital flights, could safely carry a human passenger to orbit. On February 20th, 1962, John Glenn became the first American to orbit Earth, launched aboard Friendship 7 for a mission that would complete 3 orbits before returning to Earth. Glenn's flight captured American attention even more intensely than Shepard's had, partly because it matched the Soviet achievement of orbital flight, partly because of Glenn's own charisma and articulate descriptions of his experience, and partly because of a tense moment during the mission when ground controllers received indications that the spacecraft's heat shield might have come loose. This malfunction, if real, would have meant Glenn would burn up during re-entry when atmospheric friction heated the spacecraft to over 3,000 degrees Fahrenheit. Controllers decided not to jettison the retro-rocket package after the de-orbit burn, hoping it would hold the heat shield in place if the indication was accurate. Glenn survived re-entry successfully, and post-flight inspection revealed that the warning had been caused by a faulty sensor rather than an actual problem. But those minutes of uncertainty reminded everyone of how narrow the margin for error remained in these early space flights. Glenn's safe return sparked celebrations across America and transformed him into a national hero whose fame would eventually carry him into politics and back to space nearly 4 decades later as the oldest person ever to fly in space. The early successes of human spaceflight, dramatic as they were, represented only preliminary steps toward the ultimate goal that both nations were beginning to contemplate seriously: landing humans on the moon and returning them safely to Earth. This ambition, which would have seemed like pure fantasy just a decade earlier, had entered the realm of serious planning by the early 1960s, driven by the competitive dynamics of the Cold War and by a growing recognition that space achievements had become a crucial measure of national prestige and technological capability. For the United States, the string of Soviet firsts in space had created a sense of urgency that extended beyond the space program itself, raising questions about American education, scientific research, and the nation's ability to compete in an increasingly technological world. It was in this context of concern and competitive spirit that President John F. Kennedy made a decision that would define the space race for the remainder of the decade and commit the United States to an undertaking of unprecedented scope and ambition. On May 25, 1961, less than 3 weeks after Alan Shepard's suborbital flight and little more than a month after Gagarin's orbital mission, Kennedy addressed a joint session of Congress with a special message on urgent national needs. Among various domestic and international challenges he discussed, Kennedy devoted a significant portion of his speech to space exploration, arguing that the time had come for America to take a clearly leading role in space achievement. Then he issued the challenge that would define NASA's mission for the next 8 years, declaring that the nation should commit itself to achieving the goal, before the decade was out, of landing a man on the moon and returning him safely to Earth. Kennedy acknowledged that this would not be easy or inexpensive, that it would require new spacecraft, new rockets, new mission control facilities, and new technologies that did not yet exist. He emphasized that no single space project would be more impressive to mankind or more important for the long-range exploration of space, and that none would be so difficult or expensive to accomplish. The gauntlet had been thrown down, not just to the Soviet Union, but to NASA and the American scientific and engineering communities. Kennedy's moon commitment was not made lightly or impulsively, but reflected careful consultation with NASA leadership and his science advisors about what goals were achievable and what would most effectively demonstrate American technological capability. The choice of a lunar landing was strategic, representing a goal that would require developing entirely new capabilities rather than simply improving existing ones, potentially allowing America to leapfrog past the Soviet lead in rocket power and space experience. NASA Administrator James Webb and his team believed that while the Soviets currently possessed more powerful rockets and more orbital experience, the complexity of a lunar mission would demand advances in guidance systems, spacecraft design, and mission planning, where American strengths in electronics and systems engineering might prove decisive. The moon landing goal also had the advantage of being clearly defined and dramatic, a finish line that the public could understand, and that would leave no ambiguity about which nation had won this particular race. The commitment to reach the moon before 1970 set in motion an enormous mobilization of resources, talent, and effort. NASA's budget increased dramatically through the mid-1960s, eventually consuming nearly 5% of the entire federal budget at its peak, a level of spending on civilian space exploration that has never been approached since. The agency expanded rapidly, hiring thousands of engineers, scientists, technicians, and support staff. Major contractors like North American Aviation, Grumman, Boeing, and IBM were brought in to design and build spacecraft components, rockets, and the computer systems that would guide missions to the moon. New facilities were constructed, including the massive vehicle assembly building at Cape Kennedy, where moon rockets would be assembled vertically in a structure so large it generated its own weather patterns, with clouds sometimes forming near the ceiling. Mission Control in Houston became the nerve center, where flight controllers would monitor and direct lunar missions, while the Marshall Space Flight Center in Huntsville, Alabama, under Wernher von Braun's direction, took responsibility for developing the enormous rockets that would be needed to send spacecraft to the moon. The Soviet Union, observing Kennedy's commitment and America's mobilization, faced a crucial decision about how to respond. The Soviet space program had demonstrated consistent capability to achieve firsts, but a moon landing would require resources and sustained effort on a scale that would strain even the Soviet economy. Korolev advocated strongly for a Soviet lunar program, proposing missions that would orbit the moon with cosmonauts and eventually land them on the surface. However, the Soviet system's fragmentation of authority and resources between competing design bureaus, military requirements, and political priorities made it difficult to achieve the kind of focused national commitment that Kennedy had secured for the American program. Additionally, the Soviet Union faced a critical limitation in rocket power. While their existing R-7 and its derivatives were more powerful than current American rockets, they would not be sufficient for direct lunar missions, and development of truly enormous boosters, comparable to what the Americans were planning, would require years of effort and enormous resources. Through the early and middle 1960s, both space programs continued incremental advances in Earth orbit even as they worked toward lunar missions. The Soviets achieved another first in August 1962, when they launched 2 Vostok spacecraft on consecutive days, with cosmonauts Andriy Nikolaev and Pavel Popovich conducting the first dual mission, their spacecraft passing within a few miles of each other at one point, though they lacked the capability to actually dock or rendezvous. The following year brought another propaganda victory when the Soviets launched Valentina Tereshkova aboard Vostok 6, making her the first woman in space and demonstrating Soviet commitment to gender equality, at least symbolically, since it would be nearly 2 decades before another Soviet woman flew in space. The American Mercury program concluded with Gordon Cooper's 22-orbit mission in May 1963, the longest and most ambitious Mercury flight, which demonstrated that American spacecraft and astronauts could handle extended missions with increasing confidence. Both programs recognized that reaching the moon would require capabilities that went far beyond simply staying in Earth orbit for longer periods. Spacecraft would need to rendezvous and dock in orbit, a complex maneuver requiring precise navigation and control. Astronauts would need to conduct spacewalks to practice the kinds of activities that lunar exploration would demand. Mission durations would need to extend to the week or more required for a journey to the moon and back. Communication systems would need to function reliably across the vast gulf between Earth and Moon. life support systems would need to sustain crews for extended periods. And perhaps most critically, entirely new spacecraft designs would be needed, since the simple capsules of Mercury and Vostok, adequate for brief orbital missions, were completely unsuited for the complexity and duration of lunar voyages. The race was entering a new phase, one that would test the capabilities and determination of both nations far more severely than anything they had yet attempted. The transition from simple orbital flights to missions capable of reaching the moon required intermediate steps, programs that would develop and test the techniques and technologies essential for lunar voyages. For the United States, this intermediate phase was embodied in Project Gemini, a program designed to bridge the gap between the single-seat Mercury capsules and the three-person Apollo spacecraft that would eventually carry astronauts to the moon. The Gemini spacecraft represented a significant advance in capability, carrying 2 astronauts in a cabin only slightly larger than a telephone booth, equipped with systems for maneuvering in orbit, changing orbital altitude and inclination, and practicing the delicate art of rendezvous and docking with other spacecraft. These capabilities were absolutely essential for the lunar landing mission that NASA was planning, which would require spacecraft to separate, maneuver independently, and then rejoin in lunar orbit, a complex orbital ballet that had never been attempted and whose difficulty was initially underestimated by many engineers. The first manned Gemini mission flew in March 1965, with astronauts Gus Grissom and John Young completing 3 orbits in a flight that tested the spacecraft's systems and demonstrated its improved maneuverability compared to Mercury. 3 months later, Gemini 4 achieved another American first when astronaut Ed White conducted the first American spacewalk, opening his hatch and floating outside the spacecraft for about 20 minutes while connected by an umbilical tether that provided oxygen and communications. White's spacewalk, or extravehicular activity as NASA termed it, revealed both the exhilaration and the unexpected difficulties of working in the vacuum of space. White found movement and control more challenging than anticipated, struggling to maintain his position and to perform simple tasks that would have been trivial on Earth. When the time came to return inside, he expressed genuine reluctance, finding the experience so captivating that he later described the order to re-enter as the saddest moment of his life. Yet his spacewalk also demonstrated that humans could function outside their spacecraft, a capability that would prove essential for lunar surface exploration. The Soviets had actually achieved the first spacewalk 3 months before White, when cosmonaut Alexei Leonov ventured outside Voskhod 2 in March 1965, though his experience was considerably more harrowing than the Soviets initially revealed. Leonov's spacesuit ballooned in the vacuum of space, becoming so rigid that he found himself unable to re-enter the spacecraft's airlock. In a desperate measure that violated emission protocols, Leonov partially depressurized his suit to make it flexible enough to squeeze back inside, risking decompression sickness and other physiological dangers. He succeeded in returning safely, but the incident highlighted the very real hazards of spacewalking and the many unforeseen challenges that working in space presented. The Voskhod program itself represented something of a dead end for the Soviet space effort, a stopgap design that modified the earlier Vostok spacecraft to carry multiple cosmonauts, but lacked the sophisticated maneuvering and life support systems that would be needed for lunar missions. The Gemini program progressed through a series of increasingly ambitious missions that systematically developed the techniques needed for Apollo. Gemini 5, flown in August 1965, extended mission duration to 8 days, demonstrating that astronauts could endure the confinement and physical stresses of a week-long mission comparable to the time required for a lunar journey. Gemini 6 and 7, flying simultaneously in December 1965, achieved the first true rendezvous in space, when the two spacecraft maneuvered to within a few feet of each other and maintained formation, their crews observing each other through their windows and conducting various tests. This achievement was particularly significant because the Soviets had claimed their earlier dual flights as rendezvous, though in reality those spacecraft had no ability to adjust their orbits to actually meet. The precision required for true rendezvous was extraordinary, demanding accurate knowledge of both the spacecraft's positions and velocities, careful planning of thruster burns, and delicate hand control during the final approach. NASA's success in developing these techniques represented a genuine advance past Soviet capabilities for the first time in the space race. Subsequent Gemini missions practiced docking with unmanned target vehicles, conducted longer and more complex spacewalks, and refined the procedures for orbital maneuvering. Gemini 8, flown by Neil Armstrong and David Scott in March 1966, achieved the first docking with another spacecraft, but then experienced a thruster malfunction that sent the docked vehicles into a violent tumbling spin. Armstrong managed to regain control by shutting down the maneuvering system and using re-entry thrusters instead, but the incident forced an early end to the mission and provided a stark reminder that spaceflight remained dangerous, despite increasing experience and confidence. Gemini 9 encountered frustrations when its docking target's protective shroud failed to jettison properly, preventing docking practice, though astronaut Gene Cernan did conduct a spacewalk that proved far more exhausting and difficult than planned, as he struggled with tasks and found his visor fogging from the heat his exertions generated inside his suit. The later Gemini missions achieved increasing success with spacewalking techniques as NASA learned to provide better handholds and restraints and to plan activities more carefully to avoid overtaxing astronauts. Gemini 10, 11 and 12 in the summer and fall of 1966 conducted successful docking operations, multiple spacewalks, and demonstrations of various orbital maneuvers, including using a dock target vehicle's propulsion system to boost to higher altitudes. By the time Gemini 12 splashed down in November 1966, NASA had accomplished everything it set out to do with the program, having demonstrated rendezvous, docking, spacewalking, and long-duration flight. The astronauts who flew these missions formed the core of experienced space travelers who would later command and crew Apollo missions, bringing with them hard-won knowledge of spaceflight's realities. While the United States was methodically working through the Gemini program, the Soviet space effort was experiencing difficulties that were not apparent to outside observers. Korolev was pushing his team to develop the Soyuz spacecraft, a sophisticated vehicle intended to support missions around the Moon and eventually to the lunar surface. But the program faced technical challenges and resource limitations. More seriously, the Soviet leadership had not fully committed to a moon landing program with the single-minded focus that characterized the American effort, partly because of competing military space priorities and partly because of bureaucratic rivalries between different design bureaus. Then, in January 1966, Sergei Korolev died unexpectedly during what should have been routine surgery, depriving the Soviet program of its driving visionary and most effective advocate. His death marked a turning point after which the Soviet lunar program would struggle increasingly to match American progress, though this would not become fully apparent for several more years. The space race was shifting in a fundamental way as American methodical progress began to close the gap with Soviet achievements and to develop capabilities that would prove decisive in the challenge that still lay ahead. The Moon itself, that pale companion that has hung in Earth's sky throughout human history, became the subject of intense scientific scrutiny as both space programs worked toward landing humans on its surface. Before astronauts could be sent on such a journey, engineers and mission planners needed to answer fundamental questions about the lunar environment. Was the surface solid enough to support a landing spacecraft, or would it sink into deep deposits of dust accumulated over billions of years of meteorite impacts? What were the precise characteristics of the lunar soil's composition and bearing strength? How would the extreme temperature variations between lunar day and night affect spacecraft systems and spacesuits? Where on the vast lunar surface would be the safest and most scientifically valuable sites for landing? To answer these questions, both nations launched series of robotic probes to photograph, measure, and in some cases actually touch down on the moon, gathering the data that would make human landings possible. The American effort to survey the moon proceeded through 3 overlapping programs, each progressively more sophisticated. The Ranger program sent spacecraft on impact trajectories, capturing close-up photographs during the final minutes before crashing into the lunar surface. After frustrating early failures, Rangers 7, 8 and 9 in 1964 and 1965 returned thousands of images that revealed the moon's surface in unprecedented detail, showing that even the apparently smooth Maria were heavily pockmarked with craters of all sizes, from tiny pits to massive formations miles across. These images helped eliminate some concerns about the surface, but raised new questions about the exact nature of the lunar soil. The Lunar Orbiter program followed, sending 5 spacecraft into orbit around the moon between 1966 and 1967 to photograph potential landing sites and to map the lunar surface comprehensively. These missions returned spectacular images, including the famous Earthrise photograph, showing Earth hovering above the lunar horizon, a view that captured imaginations and would later become an iconic symbol of the environmental movement. Most crucially, the Surveyor program landed spacecraft softly on the lunar surface to directly test the soil's properties and to demonstrate that controlled landings were possible. Surveyor 1 touched down in June 1966, settling gently onto the lunar surface in the ocean of storms, and immediately sending back images showing its footpads resting on firm ground rather than sinking into deep dust. The spacecraft's instruments analysed the soil composition, tested its bearing strength, and measured temperatures, radiation levels, and other environmental factors. 5 more Surveyor missions followed over the next 2 years, landing in different regions and in some cases carrying more sophisticated instruments, including a mechanical scoop that could dig trenches and test the soil's physical properties. These missions revealed that the lunar surface was covered in a layer of fine-grained regolith, pulverized rock created by eons of meteorite bombardment, but that this material had sufficient cohesion and bearing strength to support spacecraft and astronauts. The danger of sinking into lunar quicksand, a genuine concern that had troubled mission planners, was essentially eliminated. The Soviet lunar exploration program achieved its own successes during this period, though with less consistent results than the American effort. The lunar series of spacecraft attempted both orbiters and landers, with Luna 9 in February 1966 achieving the first soft landing on the moon, beating Surveyor 1 by 4 months and sending back the first images ever taken from the lunar surface. These images showed a rocky landscape and confirmed that the surface was solid, providing the same crucial data about landing feasibility that the Surveyor program would later gather in more detail. Luna 10 became the first spacecraft to orbit the moon in April 1966, and subsequent lunar missions continued to study the moon from orbit and from the surface. However, the Soviet program experienced numerous failures interspersed with these successes, and unlike the American program, it was not clearly focused on gathering specific data needed for human landing missions, reflecting the ongoing uncertainty within Soviet leadership about whether to fully commit to competing with the American moon landing goal. As data from these robotic missions accumulated, NASA mission planners worked on the complex challenge of designing a lunar landing mission profile. The most straightforward approach would be direct ascent, launching a spacecraft from Earth with enough fuel to travel to the Moon, land, and then return directly home. However, the rocket required for such a mission would need to be impossibly large, with 1960s technology, and even the enormous Saturn V rocket that was under development would fall far short of the necessary capability. An alternative was Earth Orbit Rendezvous, where multiple rockets would launch components into Earth orbit, assemble them there, and then send the assembled spacecraft to the Moon. This approach solved the rocket size problem, but introduced enormous complexity in orbital assembly and created tight launch windows and logistical challenges. The solution that NASA ultimately adopted, largely due to the advocacy of engineer John Houbolt, was Lunar Orbit Rendezvous, a mission mode that seemed counterintuitive at first, but offered decisive advantages. Lunar Orbit Rendezvous involved launching a single large rocket that would send a combined spacecraft to the Moon, but instead of landing the entire vehicle, a small specialized lunar module would separate and descend to the surface, while the main spacecraft remained in orbit. After surface exploration, the lunar module's upper stage would launch from the Moon carrying the astronauts, rendezvous with the orbiting command module, and transfer the crew back for the return to Earth. This approach minimized the mass that needed to land and launch from the Moon, since the command module with its heat shield and Earth re-entry systems could remain safely in orbit. It required developing two separate spacecraft and demanded confidence in rendezvous and docking techniques, but it made a Moon landing achievable with a single Saturn V launch. The decision to pursue Lunar Orbit Rendezvous was not made lightly, facing considerable skepticism from some engineers who worried about the risks of having astronauts dependent on a rendezvous in lunar orbit with no possibility of rescue if something went wrong. Yet the mathematics and engineering analysis clearly showed that this was the only practical path to landing on the Moon before Kennedy's end-of-decade deadline. The Lunar Orbit Rendezvous decision shaped the design of the Apollo spacecraft, which would actually consist of three components. The conical command module, where astronauts would live during most of the mission, the cylindrical service module containing propulsion, power, and life support systems, and the spider-like lunar module designed purely for operating in the vacuum of space and the Moon's weak gravity. Each of these spacecraft represented an engineering challenge of remarkable complexity, pushing the boundaries of materials science, guidance and control systems, and life support technology. As the 1960s progressed past their midpoint, the pieces were falling into place for an attempt at the Moon, but enormous work remained, and the deadline that Kennedy had set was drawing steadily closer with the inexorable passage of time. The rocket that would carry Apollo astronauts to the Moon, the Saturn V, represented an achievement in engineering that remains impressive even decades later, a machine of such scale and power that it stretched contemporary technology to its absolute limits. Standing 363 feet tall, taller than a 30-story building, and weighing over 6 million pounds when fully fueled, the Saturn V was and remains the most powerful rocket ever to fly successfully. Its development consumed an enormous portion of NASA's budget and required solving countless technical problems, from designing engines that could withstand the extreme temperatures and pressures of combustion to creating fuel pumps that could move thousands of gallons of propellant per second to building structures strong enough to contain these forces without adding crippling weight. Wernher von Braun's team at the Marshall Space Flight Center led the development effort, drawing on their decades of experience with rockets, but facing challenges that dwarfed anything they had previously attempted. The Saturn V consisted of 3 stages, each a complete rocket in its own right, stacked vertically and designed to fire in sequence. The first stage, designated SIC, was powered by 5 F1 engines, each producing over 1.5 million pounds of thrust by burning refined kerosene and liquid oxygen at a prodigious rate. These engines, among the largest and most powerful rocket engines ever built, faced extraordinary engineering challenges in their development. The combustion process was so intense and violent that early test engines experienced catastrophic instabilities, where pressure oscillations would build until the engine tore itself apart. Engineers spent years understanding and solving these combustion instability problems, eventually developing solutions that included carefully designed baffles and injector patterns that damped out oscillations before they could grow destructive. The first stage burned for just 2.5 minutes, consuming nearly 5 million pounds of propellant to accelerate the rocket to nearly 6,000 miles per hour and lift it to an altitude of about 40 miles before separating and falling into the Atlantic Ocean. The second stage, the S2, represented perhaps an even greater technical challenge despite its smaller size. This stage used liquid hydrogen as fuel, a propellant that offers excellent performance but creates enormous difficulties because it must be kept at temperatures below -400 degrees Fahrenheit to remain liquid. The Stages 5 J2 engines were marvels of cryogenic engineering, and the fuel tanks themselves required innovative insulation and structural design to contain the super cold hydrogen while remaining light enough to fly. The second stage burned for approximately 6 minutes, taking the Apollo spacecraft from the edge of space to the threshold of orbital velocity before separating. The third stage, the S4B, used a single J2 engine and served double duty, first placing the spacecraft into Earth parking orbit, and then, after the astronauts checked out their systems and confirmed readiness, reigniting to provide the final push that would send them toward the moon in what was called the translunar injection burn. Testing the Saturn V required building entirely new infrastructure. The Vehicle Assembly Building at Kennedy Space Center, where the rocket would be assembled vertically, became one of the largest buildings in the world by volume, so vast that workers moved around inside on bicycles, and special air handling systems were needed to prevent clouds from forming under the roof. The crawler transporter that would carry the assembled rocket from the assembly building to the launch pad was itself an engineering marvel. A tracked vehicle the size of a baseball infield, capable of carrying loads of over 12 million pounds while moving at the stately pace of about 1 mile per hour. The launch pad itself required flame trenches to divert the enormous exhaust from the first stage engines, sound suppression systems that would drench the pad with thousands of gallons of water to prevent acoustic energy from damaging the rocket, and umbilical towers that would supply propellants, electrical power, and breathing air to the spacecraft until the final moments before launch. The first unmanned test flight of the Saturn V, Apollo 4 in November 1967, was an event of considerable tension for NASA and for von Braun's team. The rocket performed almost flawlessly, validating years of development work and demonstrating that the vehicle could function as designed. The sound and fury of the launch was overwhelming even from miles away, with observers reporting that the noise was not just heard but felt as a physical pressure, that buildings shook and loose objects rattled, that the flame from the first stage engines was so intensely bright it seemed almost impossible to look at directly. The shockwaves from the launch set off car alarms and rattled windows for miles around Cape Kennedy. 2 more unmanned test flights followed, Apollo 5 testing the lunar module, and Apollo 6 conducting another full Saturn V test that revealed some problems with engine vibrations and other issues, but still demonstrated sufficient capability to proceed with manned missions. The Saturn V's reliability would prove remarkable, with all 13 launches that carried crews or major payloads succeeding without a single failure of the rocket itself, a record that speaks to the thoroughness of its design and testing. Yet this reliability came at enormous cost, not just in money, but in the painstaking attention to detail that characterized every aspect of its development. Every component was tested repeatedly, every system analyzed exhaustively, every potential failure mode explored and addressed. The rocket's success was built on the unglamorous foundation of rigorous engineering discipline, of test programs that caught problems before they could cause disasters, of documentation so thorough that the specifications and procedures filled rooms with paper. In an age before modern computer-aided design and analysis, much of this work was done by hand, by slide rule and calculator, by engineers working long hours and checking each other's calculations to ensure accuracy. The Saturn V represented not just technological capability, but a certain kind of organized human effort, a marshalling of resources and talent toward a single clear goal that was perhaps only possible in that particular moment of history, when the Cold War competition created both urgency and willingness to bear enormous costs for symbolic and strategic advantage. The development of the Apollo spacecraft itself, the vehicles that would actually carry astronauts to the moon and back, proceeded in parallel with the Saturn V rocket program and presented its own formidable array of challenges. The command module, a cone-shaped capsule about 11 feet tall and 13 feet in diameter at its base, would serve as home for 3 astronauts during most of the lunar journey, providing living quarters, flight controls, navigation equipment, and the heat shield that would protect the crew during their fiery return through Earth's atmosphere. Despite its small size, the command module was extraordinarily complex, packed with systems for life support, communications, guidance and navigation, propulsion control, and electrical power. Every cubic inch of space was utilized, with equipment mounted on walls and ceilings, storage lockers fitted into every available gap, and the astronauts' couches designed to fold and move to provide access to equipment behind and beneath them. The interior, though cramped, represented the pinnacle of 1960s aerospace engineering, filled with switches, circuit breakers, displays and instruments that the astronauts would need to monitor and control throughout their mission. The command module's heat shield deserved particular attention, as it would need to protect the crew during re-entry when friction with Earth's atmosphere would heat the spacecraft's exterior to temperatures approaching 5,000 degrees Fahrenheit, hot enough to melt most metals and to vaporize many materials. The shield used an ablative design covered with a material that would char and burn away in a controlled fashion, carrying heat away from the structure beneath. The exact composition and application of this ablative material required extensive research and testing, including subjecting sample heat shields to the intense thermal environments created by arc jet facilities that could replicate re-entry conditions. The shield's design had to account for the asymmetric heating that would occur as the capsule descended at an angle, entering the atmosphere at over 25,000 miles per hour and gradually slowing through atmospheric drag until parachutes could be deployed for the final descent to splashdown in the ocean. Attached to the command module's base during most of the mission was the service module, an unpressurized cylinder containing the main propulsion system, fuel cells for electrical power, oxygen and hydrogen tanks, and various other systems. The service module's engine, though much smaller than the Saturn V's massive motors, was critical for entering and leaving lunar orbit and for making trajectory corrections during the journey. This engine needed to be extraordinarily reliable, since a failure to ignite for the return journey from lunar orbit would strand the astronauts in space with no possibility of rescue. The engine's design emphasized simplicity and redundancy where possible, and it was tested exhaustively in vacuum chambers that simulated the space environment. The service module also carried radiators to dissipate waste heat from the spacecraft's systems, since in the vacuum of space, heat could only be eliminated through radiation, not through convection as it would be in an atmosphere. The lunar module represented perhaps the most unusual and specialized spacecraft ever designed, optimized entirely for operating in the moon's weak gravity and the vacuum of space with no consideration for aerodynamics or atmospheric flight. Its appearance reflected this specialized purpose, resembling some kind of ungainly mechanical insect with spindly legs, angular surfaces covered in reflective foil, and various protrusions and antennas jutting at odd angles. The lunar module consisted of two stages: a descent stage that would lower the astronauts to the lunar surface and serve as a launch platform, and an ascent stage that would carry them back to orbit for rendezvous with the command module. The descent stage contained the landing gear, a throttleable rocket engine for the powered descent, and fuel tanks arranged around a central structure that also provided storage space for scientific equipment and supplies that would be left on the moon. The landing gear consisted of 4 splayed legs with broad footpads, designed to distribute the spacecraft's weight over the lunar surface and to absorb the energy of landing on legs that partially crumpled like shock absorbers. The ascent stage housed the crew compartment, a cramped space where 2 astronauts would stand during landing and launch, held in place by restraints rather than seats to save weight and space. Windows provided views for the commander and pilot, though the visibility was limited and required the spacecraft to be oriented properly for the astronauts to see their landing site. The ascent stage's engine, unlike the descent engine, had no ability to throttle or restart, designed for a single burn that would lift the astronauts from the lunar surface and place them into an orbit where they could rendezvous with the command module. This engine's reliability was absolutely critical, since failure would leave the astronauts stranded on the moon with no hope of rescue, a fact that weighed heavily on the engineers responsible for its design and testing. Every component of the lunar module was designed to minimize weight, since every pound saved on the lunar module meant less fuel required for landing and launch, which in turn meant less mass that the Saturn V needed to send toward the moon. The spacecraft's skin in many areas was barely thicker than aluminum foil, adequate for the benign environment of space and the moon's surface, but startlingly fragile by earthly standards. Testing these spacecraft presented unique challenges, since many of the environments they would experience could not be fully replicated on Earth. Thermal vacuum chambers allowed testing of systems in the cold vacuum of space, but Earth's gravity meant that the lunar module's landing dynamics could only be partially simulated. NASA built special training vehicles that used jet engines to cancel most of their weight, allowing astronauts to practice the lunar landing's final moments in vehicles that handled somewhat like the actual lunar module would in the moon's 1/6 gravity. These training vehicles were notoriously difficult to fly and dangerous, with several crashes, including one that nearly killed Neil Armstrong when he ejected just moments before impact. Yet the training they provided proved invaluable, giving astronauts experience with the unique handling qualities of a vehicle operating near the boundaries of its performance envelope. As the 1960s moved towards their final years, the hardware was coming together, each component tested and refined, the systems integrated and checked, and the mission profiles rehearsed in simulators and in actual space flights. The goal that Kennedy had set was drawing closer, but the most difficult and dangerous steps still lay ahead. The path to the moon was shadowed by tragedy even before any Apollo mission could attempt a lunar landing, a stark reminder that the race to space carried very real risks that no amount of engineering rigor could entirely eliminate. On January 27, 1967, astronauts Gus Grissom, Ed White and Roger Chaffee entered their Apollo 1 command module for what was intended to be a routine ground test at Cape Kennedy, a full dress rehearsal of launch procedures with the spacecraft sealed and pressurized, but with no fuel in the Saturn rocket beneath it. The test had been plagued with communications problems and minor technical issues throughout the afternoon, frustrating the crew and the test conductors. Then, at 6:31 in the evening, just as the test was nearing completion, a spark from damaged wiring in the spacecraft's lower equipment bay ignited the pure oxygen atmosphere at higher than normal pressure, and flames erupted with horrifying speed. The astronauts tried desperately to open the hatch, but it was designed to open inward, and the fire's heat rapidly increased the internal pressure, making it impossible to move against the force holding it closed. Within seconds, the fire consumed the oxygen, and all 3 astronauts were dead, killed by toxic smoke and fumes even before the flames could reach them. The Apollo 1 fire shocked NASA and the nation, casting a pall over the space program and raising serious questions about whether the rush to meet Kennedy's deadline had led to shortcuts and oversights that cost 3 lives. The subsequent investigation revealed a spacecraft riddled with problems, from the flammable materials used extensively in the cabin to inadequate attention to preventing electrical shorts, from the complex hatch design that proved fatal to communication issues between contractors and NASA that had allowed problems to accumulate without adequate resolution. The investigation board made hundreds of recommendations for changes, and NASA embarked on an extensive redesign of the command module that would delay the program by more than a year. The new design eliminated most flammable materials, improved wiring and electrical systems, added a quick opening hatch, and changed to a mixed nitrogen-oxygen atmosphere at normal pressure for ground operations, only switching to pure oxygen at reduced pressure after launch. These changes probably saved lives on future missions, but they came at the cost of 3 astronauts who had been training for years and who understood the risks they faced, but had trusted that the engineering and safety procedures would protect them. The Soviet program experienced its own disaster just months later, when cosmonaut Vladimir Komarov launched aboard Soyuz, one in April 1967, the first flight of a new spacecraft that was intended to support Soviet lunar ambitions. The mission encountered problems almost immediately, with solar panels failing to deploy properly and attitude control issues preventing Komarov from orienting his spacecraft correctly. Ground controllers decided to abort the mission after just 1 day, but the troubles were not over. During re-entry, the main parachute failed to deploy properly, tangling and failing to slow the descent, and the backup parachute became entangled with the main chute, leaving Komarov in a spacecraft plummeting toward Earth with no functioning parachutes. He died on impact, becoming the first human to die during a space mission, and his death exposed serious problems in the Soviet program's quality control and testing procedures. The disaster effectively grounded the Soyuz program for over a year and contributed to the Soviet space effort's growing difficulties in matching American progress. These tragedies cast long shadows, but also drove both programs to greater rigor and attention to detail. When Apollo flights resumed in October 1968, with the unmanned Apollo 7 mission testing the redesigned command module in Earth orbit, every system had been scrutinized and every procedure reviewed. The mission succeeded completely, with astronauts Wally Schirra, Don Iserly, and Walt Cunningham spending 11 days in orbit, testing the spacecraft thoroughly and demonstrating that the redesign had addressed the problems that had killed their colleagues. The success restored confidence, but time was growing short if NASA was to meet Kennedy's deadline. Original plans had called for a methodical progression through increasingly complex missions, testing the lunar module in Earth orbit, then testing the complete Apollo spacecraft in high Earth orbit, and only then venturing to lunar orbit. However, delays in lunar module development threatened to push the first landing attempt into 1970, missing the deadline. NASA's leadership made a bold decision to accelerate the schedule by sending Apollo 8 directly to lunar orbit in December 1968, even though the lunar module was not ready. The mission would test the command and service modules in the lunar environment, practice navigation and communication at lunar distances, and demonstrate the procedures for lunar orbit insertion and return to Earth. The decision was controversial, representing a significant risk, but it reflected NASA's confidence in the Saturn V and Apollo spacecraft and determination to seize the initiative from the Soviets, who intelligence suggested might be planning their own manned lunar orbital mission. On December 21, 1968, astronauts Frank Borman, Jim Lovell and Bill Anders climbed aboard Apollo 8 atop a Saturn V rocket and launched toward the Moon on humanity's first journey beyond Earth orbit, leaving behind the planet where humans had evolved and always lived, venturing into deep space where no one could reach them if something went wrong. The 3-day journey to the Moon passed without major incident, though the astronauts experienced the strange sensation of watching Earth shrink behind them until it became just another celestial object, a blue and white sphere against the blackness of space. On December 24th, the spacecraft swung around the far side of the Moon, and for 34 minutes they were completely cut off from Earth, blocked by 2,000 miles of lunar rock, utterly alone in a way no humans had ever been before. When they emerged from behind the Moon, the service module's engine had successfully fired to place them into lunar orbit, and they became the first humans to see the Moon up close, to observe its mountains and craters and ancient lava plains from just 60 miles above the surface. They photographed potential landing sites, tested navigation techniques, and on Christmas Eve they conducted a television broadcast in which they showed Earth rising above the lunar horizon, a view of stunning beauty that emphasized how fragile and precious humanity's home planet appeared from 250,000 miles away. They read from the book of Genesis, and their broadcast was heard by perhaps 1 billion people around the world, the largest audience that had ever simultaneously experienced a single event. The success of Apollo 8 transformed the space race's trajectory, demonstrating American capability to reach the Moon and return safely while the Soviet program continued to struggle with technical problems and resource constraints. Through early 1969, NASA proceeded methodically through the remaining steps needed before attempting a landing. Apollo 9, launched in March, tested the lunar module in Earth orbit for the first time with a crew aboard, with astronauts Jim McDivitt and Rusty Schweickart flying the spindly spacecraft independently from the command module, checking its systems, practicing rendezvous and docking maneuvers, and demonstrating that the spacecraft could separate and rejoin as would be required in lunar orbit. Schweickart also conducted a spacewalk, testing the spacesuit that would be used on the Moon's surface and confirming that astronauts could transfer between spacecraft through the vacuum of space if an emergency made that necessary. Apollo 10, launched in May 1969, served as a full dress rehearsal for the landing mission, travelling to the Moon and entering lunar orbit, then separating the lunar module, which descended to within just 9 miles of the surface, before jettisoning the descent stage and firing its ascent engine to return to the command module. Astronauts Tom Stafford and Gene Cernan flew closer to the Moon than any humans before them, near enough to see boulders on the surface and to get a real sense of the terrain's texture and relief. They tested the radar systems that would guide the final landing, practiced the communications and navigation procedures, and verified that rendezvous in lunar orbit worked as planned. Everything functioned well except for a heart-stopping moment when the lunar module began tumbling wildly during the separation of its 2 stages, a problem caused by an incorrectly positioned switch that Stafford quickly diagnosed and corrected. The mission returned to Earth having accomplished everything except the actual landing, leaving only that final step to be attempted. The crew selected for Apollo 11, the mission that would attempt humanity's first landing on the Moon, consisted of 3 experienced astronauts who had each flown in space before, and who represented different aspects of the skills and temperaments needed for such a challenging mission. Neil Armstrong, the mission commander, was a civilian test pilot with a reputation for calm competence and an analytical mind that had served him well when dealing with emergencies, including the Gemini 8 thruster malfunction and his near-death ejection from the Lunar Landing Training Vehicle. Buzz Aldrin, the lunar module pilot who would accompany Armstrong to the surface, held a doctorate in astronautics and had written his thesis on orbital rendezvous techniques, bringing both practical flying skills and deep theoretical knowledge. Michael Collins, the command module pilot who would orbit the moon alone while his crewmates explored the surface, was known for his thoughtful nature and his skill at the complex navigation and docking maneuvers his role required. The mission launched on July 16, 1969, from Kennedy Space Center before a crowd estimated at nearly 1 million people who gathered on nearby beaches and roads to witness the spectacle. Millions more watched on television as the Saturn V lifted ponderously from the pad, balancing on a column of flame, slowly gathering speed as it climbed towards space. The launch was flawless, and the spacecraft settled into Earth orbit for systems checks before the third stage reignited to send them toward the moon. The 3-day coast to lunar orbit passed quietly, with the crew monitoring systems, conducting course corrections, and occasionally broadcasting television transmissions showing views of Earth and the spacecraft's interior. On July 19th, they swung behind the moon and fired the service module's engine to enter lunar orbit, beginning a series of orbits that would continue for more than a day while they prepared for the landing attempt. On July 20th, Armstrong and Aldrin transferred into the lunar module, separated from the command module where Collins would remain, and began their powered descent toward the Sea of Tranquility, a relatively smooth plane selected for its flatness and lack of major obstacles. The descent proceeded according to plan through its early phases, with the lunar module's engine throttling to control their rate of descent while guidance computers calculated their trajectory. Then, at about 4 minutes into the descent, alarms began sounding as the computer became overloaded with radar data, threatening to abort the landing automatically. Mission Control, after tense seconds of analysis, determined that the computer was still maintaining control despite the overload and gave permission to continue. As they descended through the final 1,000 feet, Armstrong looked ahead to their designated landing spot and saw that it was strewn with boulders, far too rough for a safe landing. He took manual control and flew the lunar module forward, searching for a smoother area, while Aldrin called out altitude and fuel remaining. The fuel situation became increasingly critical as Armstrong continued searching for a safe landing site, with Mission Control and Aldrin both aware that they had perhaps only seconds of fuel remaining before they would need to abort and return to orbit. Finally, Armstrong found a clear area, descended the last few feet, and at 4:17 p.m. Eastern Time on July 20th, 1969, the lunar module's footpad settled onto the moon's surface with fuel for perhaps 30 seconds of flight remaining. Armstrong's transmission to Earth was characteristically understated. "Houston, Tranquility Base here. The Eagle has landed." The tension that had gripped Mission Control exploded into cheers and relief. Though the astronauts and controllers all knew that landing was only half the challenge, that they still needed to launch from the moon, rendezvous with Collins, and return safely to Earth. But for this moment, after years of work and enormous investment and the sacrifice of 3 astronauts in the Apollo 1 fire, humans had reached the surface of another world, had achieved what Kennedy had challenged the nation to accomplish, and had demonstrated technological capability that even a decade earlier would have seemed like fantasy. The space race had reached its dramatic crescendo, though neither the world nor the astronauts themselves yet fully comprehended the historical magnitude of what had just occurred on that ancient airless plane nearly 250,000 miles from Earth. After landing on the Moon, Armstrong and Aldrin faced a decision about when to venture outside for their historic moonwalk. Mission planners had scheduled a sleep period before the spacewalk, reasoning that the astronauts would be exhausted from the intense concentration required during descent and landing. However, both men felt alert and eager to proceed, and Mission Control agreed to let them begin preparations for the extravehicular activity immediately. The process of donning spacesuits, checking their systems, depressurizing the lunar module's cabin, and opening the hatch took several hours. Meticulous work that could not be rushed since any error with the suits or life support systems could prove fatal. Finally, about 6.5 hours after landing, Armstrong opened the hatch and began backing out onto the small porch at the top of the lunar module's ladder, moving carefully in his bulky spacesuit through the narrow opening. The descent down the ladder took several minutes, with Armstrong pausing on each rung to test his movements in the Moon's weak gravity and to deploy a television camera that would transmit grainy black and white images of his arrival on the surface to viewers on Earth. As he reached the bottom of the ladder, he stepped onto one of the lunar module's footpads, then lowered himself down to the surface itself, and at 10:56 p.m. Eastern Time on July 20th, 1969, Neil Armstrong became the first human being to stand on another celestial body. His words, partially garbled by static but nonetheless historic, acknowledged the moment's significance. That's one small step for man, one giant leap for mankind. Armstrong had intended to say, one small step for a man, which would have made the grammar and the contrast between individual and collective achievement clearer. But in the excitement and the crackle of communications, the article was either not said or not heard, and history recorded the version that reached Earth. Armstrong spent his first minutes on the surface conducting tests and observations, describing the texture of the lunar soil, testing how his boots sank into the fine-grained regolith, and experimenting with different ways of moving in the low gravity. He found that the surface material was very fine, almost like powder in some places, but that it compressed and held together under pressure, making it supportive enough for walking, though it did tend to cling to everything it touched. About 20 minutes after Armstrong's emergence, Aldrin joined him on the surface, and the two astronauts began working through a carefully planned sequence of activities designed to make the most of their limited time outside. They unveiled a plaque mounted on the lunar module's leg, declaring that humans from planet Earth had first set foot upon the Moon and came in peace for all mankind, a sentiment that perhaps oversimplified the Cold War competition that had driven the achievement, but nevertheless captured an ideal worth expressing. The astronauts planted an American flag, struggling slightly with the task because the soil was harder beneath the surface than expected, and the pole would not penetrate as deeply as intended. The flag hung from a horizontal rod to make it visible, since there is no wind on the airless Moon to cause it to wave, though this arrangement later led to conspiracy theories from people who did not understand this detail. Armstrong and Aldrin received a telephone call from President Richard Nixon, who spoke to them from the White House in what he described as the most historic phone call ever made, though the astronauts, focused on their tasks and conscious of limited time, kept their responses brief and professional. They then set about collecting rock and soil samples, scooping material into bags, photographing the samples before collection to document where they came from, and selecting interesting rocks that might provide scientific insights into the Moon's geology and history. The scientific instruments they deployed included a seismometer to detect moonquakes and meteorite impacts, a laser-ranging retroreflector that would allow precise measurement of the Earth-Moon distance by reflecting laser beams fired from Earth, and a solar wind collector to capture particles streaming from the Sun. These instruments represented the beginning of the moon's transformation from a distant object of speculation to a place where ongoing scientific measurements and observations could occur, where instruments could gather data continuously rather than during brief flyby missions. The seismometer would continue operating for years, detecting the moon's subtle tremors and revealing that the lunar interior is less geologically active than Earth, but not entirely dead, that the moon still experiences small quakes and settling from its slowly cooling interior. The entire moonwalk lasted just under 2.5 hours, far shorter than later Apollo missions would achieve, but nonetheless sufficient to collect nearly 50 pounds of lunar samples and to conduct the planned experiments and observations. Armstrong and Aldrin found moving in the lunar gravity easier than they had anticipated, though the bulky spacesuits restricted their movements and required them to plan their actions carefully. The lack of atmosphere meant that shadows were absolutely black, with no scattered light to reveal details, creating high contrast between sunlit areas and shadow that could be disorienting. The sky above was black despite the sun's presence, since there is no atmosphere to scatter light and create the blue sky familiar on Earth. The Earth itself hung in that black sky, a brilliant blue and white sphere, about 4 times larger in appearance than the moon appears from Earth, slowly rotating to reveal different continents and oceans. As their scheduled time outside drew to a close, the astronauts climbed back up the ladder, carrying their sample boxes and making sure they had retrieved everything needed from the surface. They sealed the hatch, repressurized the cabin, and began the process of removing their suits and securing equipment for the flight back to orbit. They were scheduled to sleep before launch, but sleep proved difficult in the cramped quarters, with adrenaline still coursing through them, and the knowledge that they still faced the critical task of launching from the moon and rendezvousing with Collins, who had been orbiting alone, maintaining the command module, and photographing potential future landing sites. The lunar module's ascent stage engine, which had never been tested in the actual lunar environment, would need to fire perfectly to lift them from the surface, and unlike virtually every other rocket in spaceflight history, there was no backup, no possibility of a second attempt if something went wrong. Their lives and the mission's success depended entirely on that single engine performing flawlessly when the moment came. After a brief and restless rest period, Armstrong and Aldrin began preparations for their departure from the lunar surface, conducting system checks and aligning their guidance platform using star sightings through the lunar module's optical instruments. The ascent from the moon would be entirely automatic, controlled by the spacecraft's computer, following a precisely calculated trajectory that would place them into an orbit where they could rendezvous with Collins in the command module. Unlike launch from Earth, where rockets fight against gravity's pull through a dense atmosphere, the lunar ascent would occur in complete vacuum with gravity only 1/6 as strong, making the task mechanically simpler, but no less critical. At the designated moment, explosive bolts fired to separate the ascent stage from the descent stage, and the ascent engine ignited, pushing Armstrong and Aldrin upward from the moon on a pillar of flame that left the descent stage behind as a permanent monument to humanity's achievement, along with the footprints and equipment scattered around it. The ascent went smoothly, and within minutes they were in orbit around the moon, beginning the carefully choreographed ballet of orbital mechanics that would bring them together with Collins. The rendezvous took several hours of maneuvering, with the lunar module using its reaction control thrusters to adjust its orbit incrementally, closing the distance with the command module while matching velocities so that the final approach could be gentle and controlled. Collins, who had spent more than a day alone in lunar orbit, watching his crewmates from above and photographing the moon while waiting anxiously for their safe return, guided the command module to facilitate the docking. When the two spacecraft finally came together and locked with a solid thump, the sense of relief was palpable. Armstrong and Aldrin transferred back to the command module, along with their precious cargo of lunar samples, and the lunar module was jettisoned, left to eventually crash into the moon's surface, while the three reunited astronauts prepared for the journey home. The return to Earth required one more critical engine burn, firing the service module's engine to break free of lunar orbit and begin falling back toward Earth. This burn occurred behind the moon, out of contact with mission control, and the astronauts and controllers alike waited through the tense minutes of radio silence for the spacecraft to emerge from behind the lunar limb, either having successfully started its homeward journey or still trapped in orbit with insufficient fuel to try again. When the signal was reacquired and Collins reported that the burn had been successful, another milestone had been passed. The 3-day coast back to Earth was almost leisurely compared to the intensity of the landing and surface activities, though the crew remained busy with housekeeping tasks, course corrections, and preparations for re-entry. They also conducted television broadcasts answering questions from reporters and showing views of Earth growing larger in their windows as they approached home. Re-entry on July 24th subjected the astronauts to intense deceleration forces as the command module plunged into Earth's atmosphere at over 25,000 miles per hour, friction with air molecules heating the heat shield to temperatures that turned the surrounding air into a glowing plasma that blocked radio communications for several long minutes. The spacecraft descended under parachutes into the Pacific Ocean, where the aircraft carrier USS Hornet waited to recover them. As a precaution against the remote possibility that they had brought back lunar microorganisms that could prove harmful to Earth's biosphere, the astronauts were immediately sealed into a mobile quarantine facility, a modified trailer where they would spend the next several days before being transferred to a larger quarantine facility in Houston. This quarantine period, though it seemed excessive even at the time since the moon is almost certainly sterile, reflected careful attention to planetary protection protocols and ensured that the returning lunar explorers did not inadvertently contaminate Earth with anything they might have collected. The global reaction to Apollo 11's success was extraordinary, transcending even the Cold War divisions that had motivated the mission. Around the world, people celebrated the achievement as a triumph for humanity as a whole, not just for America or for one political system. The astronauts became instant celebrities, embarking on global goodwill tours where they were received by heads of state and cheered by enormous crowds. The lunar samples they brought back began yielding scientific insights almost immediately, revealing that the moon's rocks were ancient, some dating back more than 4 billion years to the solar system's early history, and that the moon had experienced volcanic activity in its past, but had been geologically quiet for billions of years. The rock's composition confirmed that the moon and Earth shared a common origin, supporting theories that the moon formed from debris ejected when a Mars-sized object collided with the early Earth in a catastrophic impact. Yet even as the world celebrated, NASA was already planning follow-up missions. Apollo 11 had achieved Kennedy's goal of landing humans on the moon before the decade ended, but the space agency had approval and funding for additional lunar landing missions that would conduct more extensive surface exploration and deploy more sophisticated scientific instruments. These subsequent missions would land at more challenging locations, stay longer on the surface, and eventually include a battery-powered rover that would extend the astronauts' range far beyond what walking alone could achieve. The success of Apollo 11 also effectively ended the space race in its original form, as it became clear that the Soviet Union would not be able to match the American achievement in any reasonable time frame. The Soviets had experienced repeated failures in testing their N-1 moon rocket, a massive vehicle comparable to the Saturn V, but troubled by engine problems and inadequate testing that led to several catastrophic explosions. After Apollo 11, the Soviet program quietly abandoned its manned lunar landing efforts, though this would not be officially acknowledged for many years. The technologies and techniques developed for Apollo would influence spaceflight for decades to come, from the computers and software that managed complex missions to the materials science that created lightweight, strong structures and effective heat shields. The program trained a generation of engineers and scientists who would go on to lead subsequent space initiatives and to apply their expertise to challenges beyond aerospace. Perhaps most significantly, the images of Earth taken from the Moon helped catalyze environmental awareness, showing humanity's home as a fragile oasis in the hostile emptiness of space, a perspective that contributed to the emerging environmental movement of the 1970s. The space race, which began with weapons and military rivalry, had produced something transcendent, a moment when humans looked back at their world from another celestial body and saw it with new eyes, recognizing both its beauty and its vulnerability. The legacy of the space race extended far beyond the dramatic achievement of landing humans on the Moon, radiating through technology, culture, and human consciousness in ways that continue to resonate decades later. 5 more Apollo missions successfully landed on the Moon after Apollo 11, each venturing to more challenging terrain and conducting increasingly sophisticated scientific investigations. Apollo 12 demonstrated precision landing by touching down within walking distance of an old Surveyor probe, allowing the astronauts to retrieve parts for analysis of how materials weathered in the lunar environment. Apollo 14 saw the first use of a hand-pulled cart to carry equipment and samples, extending the astronauts' range slightly beyond what they could carry on their backs. Apollo 15, 16, and 17 were extended missions that included the Lunar Roving Vehicle, a battery-powered car that allowed astronauts to travel several miles from their landing sites, dramatically expanding the area they could explore and the diversity of samples they could collect. The scientific return from these later missions proved immensely valuable, as astronauts selected by geologists collected samples from a variety of terrains, including highland regions, crater rims, and ancient volcanic deposits. The rocks they brought back told a story of the Moon's history spanning billions of years, revealing a world that had been geologically active in its youth, with extensive volcanic flooding that created the dark Maria visible from Earth, but that had cooled and quieted over time until it became the essentially dead world we see today. Analysis of impact-melted rocks allowed scientists to date major cratering events and to reconstruct the late heavy bombardment period when the inner solar system was swept by a storm of asteroids and comets that scarred the Moon and Earth alike. The seismometers deployed by various missions detected moonquakes originating deep in the lunar interior, revealing that the Moon has a small, partially molten core, unlike the completely solid body some theories had predicted. Apollo 13, the mission that never landed due to an oxygen tank explosion in the service module, paradoxically became one of the program's most celebrated missions because of the successful effort to bring the crew home safely despite catastrophic damage to their spacecraft. The explosion, which occurred 2 days into the mission while en route to the Moon, crippled the command and service modules, forcing astronauts Jim Lovell, Jack Swigert, and Fred Hayes to use the lunar module as a lifeboat for the journey around the Moon and back to Earth. Mission Control and the crew worked together to solve unprecedented problems, from removing carbon dioxide from the cabin air, using improvised filters made from duct tape and spare parts, to calculating engine burns using the lunar module systems to bring them back on a trajectory that would reach Earth. The mission's successful conclusion demonstrated not just technological capability, but also human resourcefulness and determination, the ability to improvise solutions to problems that had never been anticipated or practiced. The space race's influence on technology extended into virtually every aspect of modern life, though often in indirect ways that make the connections difficult to trace. The demands of spaceflight drove advances in miniaturization of electronics, leading to integrated circuits and microprocessors that formed the foundation for the computer revolution. Materials developed for spacecraft, including advanced alloys, ceramics, and composites, found applications in everything from aircraft to medical devices. The need for reliable computer software led to advances in programming techniques and quality assurance that influenced the entire software industry. Freeze-dried foods developed for astronauts became consumer products. Water purification systems designed for spacecraft were adapted for use in remote areas. Medical monitoring equipment developed to track astronauts' vital signs during missions led to improvements in patient monitoring in hospitals. The list of spin-off technologies is extensive, though debates continue about whether these innovations required the space program or would have emerged eventually through other channels. Perhaps more significantly than any specific technology, the space race demonstrated what could be accomplished when a clear goal was set and resources mobilized to achieve it. The success of Apollo showed that extremely complex technical challenges could be solved through systematic engineering, rigorous testing, and coordinated effort among thousands of people and hundreds of organizations. This lesson influenced approaches to other large-scale technical projects, from building particle accelerators to developing new aircraft to tackling environmental challenges. The program also inspired countless young people to pursue careers in science, engineering, and mathematics, creating a generation of technically trained professionals whose work extended far beyond aerospace. Universities expanded their engineering and science programs in response to the demand for trained personnel, and government investment in research increased substantially during the space race years, creating an infrastructure of laboratories and research centres that continued to be productive long after the moon landings ended. The space race also represented a curious channeling of Cold War competition into an arena that, while certainly connected to military capabilities through rocket technology, was fundamentally less destructive than direct military confrontation. The money spent on space programs was substantial, but modest compared to military budgets, and the achievements were in some sense shared by all humanity rather than being purely zero-sum competitions. When Armstrong and Aldrin planted the American flag on the moon, they also left a plaque stating they came in peace for all mankind, acknowledging that the achievement, however motivated by national rivalry, represented a human accomplishment transcending borders. The Soviet Union's Yuri Gagarin and America's Neil Armstrong became heroes, not just in their own countries but globally. Their achievements celebrated as expanding the boundaries of human capability rather than as victories in a conflict. The end of the Apollo program in 1972 with Apollo 17 marked a transition in spaceflight from exploration driven by geopolitical competition to more routine operations focused on scientific research and practical applications. The dramatic days of the space race gave way to an era of space stations, reusable shuttles, international cooperation, and increasingly sophisticated robotic probes exploring the solar system and beyond. The competition between superpowers evolved into collaboration, most notably in the Apollo-Soyuz joint mission of 1975, where American and Soviet spacecraft docked in orbit, symbolizing détente between the rival powers. Later, the International Space Station would become a truly multinational project, where astronauts and cosmonauts from former rival nations worked side by side, conducting research and maintaining humanity's continuous presence in space. Looking back from the vantage point of decades later, the space race appears as a unique moment in history when technological optimism, political rivalry, vast resources, and public enthusiasm converged to drive achievements that still seem remarkable. The Saturn V rockets that carried Apollo to the moon remain the most powerful vehicles ever to fly successfully, and no human has travelled beyond low Earth orbit since the last Apollo mission, a fact that sometimes prompts reflection about whether progress is always linear or whether some achievements represent peaks that are not necessarily surpassed simply because time passes. The space race left humanity with images of Earth from space that changed how we see our world, with samples of another world that continue to yield scientific insights, with technologies that permeate modern life, and with the demonstrated knowledge that humans can venture beyond Earth and return safely, a capability that may yet lead to permanent human presence beyond our home planet. The race began with weapons and fear, with competition and nationalism, but it produced something larger and more enduring, a legacy that belongs not to any single nation, but to the human species and to the continuing story of our expansion into the cosmos that surrounds our small blue world.